Welcome back, everyone. So today we're going to be talking about ensemble methods. And as the name suggests, this concerns techniques for combining models together, into one ensemble. And what we're going to see is that in the aggregate, these ensemble models are more powerful than any one such model is on its own. And so to really understand why these methods are so powerful, we need to revisit this idea of the bias variance trade-off and actually deepen our understanding of it a little bit. So you might have noticed a kind of recurring pattern in this course. We've encountered several examples now, several learning algorithms where there's been this single hyperparameter that controls its behavior along the bias variance continuum, as we called it. And we encountered these words, bias and variance, first when we looked at the k-nearest neighbors algorithm, where we could, set the number of neighbors that determined the predicted label of a test point. So these figures here are images of data sets that were passed through the KNN algorithm, presented to it, and then it spat out the corresponding decision boundary as well as predictions for test points. And so if we set the number of neighbors to 1, like in this plot on the left, this allowed the decision boundary to be flexible enough to actually have 0 error on the training data set. And so this happened because each data point was its own nearest neighbor. And so if we presented a slightly different training data set to a 1 nearest neighbor model, this fitted decision boundary shown in black here, that would change. And so these models would disagree on predictions for new test data. So if we had this 1 nearest neighbor algorithm and we trained it on one training data set, we would get 1 decision boundary. If we were to present a slightly different training data set, we would see a different decision boundary. And so that's what I mean by these models would disagree on predictions for new test data because they would have different decision boundaries. And so one model might be right about one test point, but wrong about another, and vice versa. So the other model might be wrong about one test point, but right about another. And so we characterize this situation as one with high variance. And so on the other end of the spectrum, if we aggregated over many neighbors, set k to 100, this would cause essential features of the underlying distribution to actually be ignored. And so we called this bias because it underestimated the complexity of the true underlying function. And so these models would also make errors on the test data, but they would tend to agree with each other. And so the decision boundary would be very similar from training set to training set. And in practice, we want to set k to be some modest value to be able to capture the essential features of the data set without being too sensitive to any one data point, without its decision boundary depending too much on one decision point. Data point. And we actually saw variability show up in support vector machines when we played with that hyperparameter C that controls the penalty for margin violations and misclassifications. And so when C was very large, any one training point could have a huge influence on the decision boundary. And we saw that change quite a bit from training set to training data set to training data set. And then in the dual form of the SVM, we saw that small c meant that no one data point could have a large contribution to the learned decision boundary. And so this meant that it would tolerate more margin violations and misclassifications and result in a larger margin. And so in ridge and lasso regression, we had the regularization hyperparameter lambda that penalized the norm of the weights. These figures here were taken out of the pattern recognition and machine learning text. And what the authors did was they had a collection of data sets consisting of input target pairs, using this sign function as the underlying function to generate that data. And then they corrupted those examples with noise. And then they fit linear regression models to each of those data sets using a set of fixed Gaussian basis functions over this interval 0 to 1. But then crucially, what they paid attention to was looking at what happened with different values of lambda. And so when they set lambda to a large value, the fitted models clearly failed to capture some of the essential features of the true underlying function, like in this plot here, where lambda was set to 15. But we can see that in this case, the models were pretty consistent with one another. So each red line here indicates one fit to the data generated by corrupted samples from this sign function. And then on the other hand, if they set lambda to be small, this allowed models to pick up on patterns that weren't actually there, weren't actually essential to this true underlying function, or didn't correspond to actual features of the true underlying function. And so regardless of the model, take a step back. In all of these cases, in these three cases that we've talked about so far today, we've generally left the selection of this hyperparameter to cross-validation to see how a particular choice affects the model's ability to generalize to unseen data. And then we've been selecting a single best model to tell us how to make predictions going forward. So there's actually a very fundamental reason why we've been seeing this trade-off between bias and variance, why it's come up so many times in this course. And it's because they have a mathematical relationship through the test error. And so to see why, let's consider a regression problem where we want to predict some continuous random variable y. And so this y, they're noisy observations of some unknown function f of another random variable x. And in this setup, our predictions can never be perfect because there is noise that we don't model, epsilon. And so if our goal is to minimize the mean squared error, could we say anything about the nature of the error we would expect on some test input? And so the expected prediction error of a regression fit f hat of x at an input point x of t is the difference between the target y and the prediction all squared. And so yeah, this is effectively saying if we were to fit a bunch of models, what error would we expect to see for some arbitrary input x of t? And so the proof of this is actually on assignment 3. But it turns out that this error can actually be decomposed into 3 terms. And so in essence, we can think about the total error on the test error, as the sum of 3 kinds of error. And so that's in this line here. So this first term, that's simply the variance of the noise. This is the randomness beyond the scope of the function we're trying to approximate, and no model can get rid of. This second term concerns the difference between the expected value over our predictions and the true underlying function. So this is asking, what the model tends to do on average, and then comparing that to reality. And so this is the meaning of bias. And then this last term, we take the expectation of the squared differences between a particular, we take the expectation of these squared differences between model a particular prediction, f hat of x of t, and the average over predictions. So we're interested in how different a particular model is from what the others have tended to do on average. And so this is precisely the definition of variance. Right, and so, yeah, so if you have trouble following along, these So kind of key here. And so the figure on the right here illustrates this idea. And so as model complexity increases, depicted by degrees of freedom, df as the x-axis here. The training error associated with the fitted models, just shown in blue, that reduces consistently. So as the model complexity increases, we can always count on seeing a corresponding decrease in the training error in the aggregate. On the test error in red, though, we see an initial drop initially, but then it starts to rise again. And so this is because at some point, the model gets so flexible that it starts to overfit the training data. And this is going to lead to high variance on new data. And so as we increase complexity by changing the hyperparameter, like increasing the number of features or the depth of the tree, this is going to cause the variance of predictions to increase and contribute to the error. And so even though this allows the model to perform better on the training data set, it can hurt the model's ability to generalize to unseen data, which increases the test error. And so because we only have one hyperparameter to play with, if the variance is initially very high, we need to be willing to tolerate some bias in order to improve performance. So yeah, at a high level, what we've been doing during cross-validation is that we've been searching for the hyperparameter that gives us the lowest error on the validation fold on average, or the lowest generalization error. And so we've been searching for this sweet spot between bias and variance. And so another way to think about this is characterizing models by the extent to which they're biased and variable, respectively. So we can drop our favorite 2x2, but bias on one axis and variance on another. And so on the extreme end of the spectrum is, kind of a worst case scenario. Here, our model is both biased and variable, so it somehow manages to underfit while also being sensitive to fluctuations in its training data. This could happen if we're in a situation, a data poor situation, or maybe we're working with the wrong hypothesis class. And so but the regions that we've been exploring are typically either biased or variable. And so we've been either high bias but low variance, like k nearest neighbors with a k of 100, or low bias, high variability, for example, with k of equal to 1. So yeah, the regions that we've been exploring are one of these cases. And we've been trying to find that sweet spot through cross-validation that minimizes the test error by tolerating a bit of both. Now, of course, the ideal situation would be to have low bias and low variance. We want to make near perfect predictions, and we would like to do that almost all of the time. But this isn't really something we can do with the models we've encountered so far. With that single hyperparameter, we have to tolerate some bias and some variance to optimize the overall error. And so this is the basic strategy we've been following, and it's gotten us quite far. However, we seem to have found a ceiling, for how good our models can be. There's this performance regime that appears to be just outside of our reach because we're stuck just trading off bias and variance against one another to try to find a balance that does its best. And so at this point, it's worth asking, like, is this really the best we can do? And so, we seem to have hit a bit of a wall. And at this point, it's helpful to just take a step back and think about, what we're doing, what we've really been doing in this course, really at a high level. And so for most of this course, we've been getting this batch of data, and then we've been fitting a single model to it. And then we've been relying on that single model for all of our predictions going forward. it's just so different from how we approach problems in everyday life. Uh, you know, for example, suppose you were, buying, lots of you have cats at home. Maybe you're considering buying a new cat tree for one of your cats, or just maybe you only have one cat. But I'd be willing to bet that most of you, if you were considering buying a product, would go straight to Amazon to look at the reviews. And you wouldn't just read one review. You would want to read multiple reviews. Because one reviewer might highlight the strengths of a particular product over other options that are out there. And then another might reveal hidden flaws that might only come up in a few isolated use cases. But together, they're giving you a fuller picture of the product that you're considering spending your money on. Similarly, maybe if you started not feeling too great, one of the first things that you would do is reach out to your general practitioner. And they could make an initial assessment, maybe narrow down some plausible causes for your symptoms. But they may need to refer you to a specialist to make a more refined diagnosis. And then that specialist might order tests that get you to work with some lab technicians. And so by the end of this process, you actually end up engaging with a healthcare team. But together, they provide better care than any one member could on their own. And so there is an analog of this kind of collaboration in machine learning, and it's called ensemble methods, which is the main topic today. And so these are strategies that combine multiple models to improve overall performance. And so there's two main ways to build an ensemble, in parallel and sequentially. And so in the parallel case, we're given a batch of data, and then we train up several copies of the model based on slightly different versions of that original data set. So yeah, some samples might be missing or appear more often one time than another, shown by darker or lighter shades of gray. And then each of those copies of the model then contribute to the final prediction. And so it turns out that building a model in this way tends to reduce the variance. Tends to reduce the variance of an ensemble as compared to the variance of any one of its component models. And then the other way to build an ensemble is sequentially. And so this is analogous to the medical diagnosis situation where the healthcare professional that we were working with recruited another professional to handle a situation beyond their expertise, and they might recruit someone else. And so in this situation, the base or lower level classifiers are actually trained in sequence. So we're given a batch of data, and then we create one low level model or base model, base learner, and each and then the next we create another one based on the output or performance of the last one. And so these are built sequentially with the idea that each new model that we add to the ensemble fills in for what the previous ensemble, for what the previous base learner couldn't handle. And so it turns out that this strategy actually focuses on alleviating bias in the overall model. All similar to the parallel situation, however, all such base learners do contribute to the final prediction, but the manner in which this is they're aggregated is a little bit more nuanced, and we'll get into that later. All right. So today we're going to talk about each of these in turn. Um, so we'll start off by talking about how we build ensembles to reduce variance, what specifically that looks like. We'll then talk about ensembles that can reduce bias, and then finally we'll do a brief comparison between these two. All right. So to give an example of how an ensemble could reduce variance, let's start with the simple example of estimating the mean of a distribution. So let's imagine we have a bunch of independent and identically drawn samples. We'll call them x1 through x1, x2, xn. And so these are all drawn from a normal distribution with a simple scalar mean of mu and a scalar variance of sigma. So this is a one-dimensional Gaussian distribution. So and yeah, our goal is to estimate the mean of that distribution. So a natural way to do this is to take the empirical mean, and that's just going to be the average over all samples. So we'll denote this as mu hat, and it's calculated by summing up all of the samples and then dividing by the total number of samples. So that shouldn't be a surprise to anyone. But the good news is that this empirical mean is an unbiased estimate. And so that means that the expectation of our estimator is going to converge to the true mean in the limit of an infinite number of samples. And so now we can talk about the variance of this estimator. So the variance of mu hat, that tells us how much our estimate is likely to fluctuate around the true mean across different sample sets. And so using some properties of variance, we can figure out what this actually looks like. Due to the scaling property of variance, the variance of a scaled average like this ends up being the variance of each individual sample, sigma squared, divided by the number of samples. And so since each xi is independent with the same variance sigma squared, the math works out cleanly like this. And so yeah, we can see that the variance of our estimate is inversely proportional to the number of samples that we have. So as we collect more data, this estimate of the mean, that's going to become more stable. So we're going to become more confident that our sample mean is close to the true mean. So I mentioned in the introduction that the ensembles are a collection of models. So let's explore what could happen if we actually had enough data to make several estimators of the mean. So in that case, we could construct several groups, let's say B groups of data. And so each group, S1, S2, all the way up to SB, that would contain n data points. And so for each of these groups, we can compute an individual mean estimate, and we'll call that mu hat sub B. And then if we take the average of these B estimates, we'll get an overall ensemble mean, and we'll call that mu hat sub large B. And the nice thing is that this ensemble mean is still an unbiased estimate of the true mean mu. And so what this means is that on average, it's going to give us the correct answer. But the real magic lies in what happens to the variance of the estimate. And so because of the scaling property of variance, when we take the variance of our ensemble mean, mu hat B, we're going to get this 1 over B squared factor outside. And then because as each estimator is independent and would have the same variance, the variance of this sum is simply B times the variance of one estimator. And which we know from before that this is sigma squared over n. So the new variance of the ensemble is simply sigma squared over bn. And so this means that by forming B separate estimates and then averaging them, we can reduce the variance by a factor of b. And so we would be able to reduce the variance of our estimate b-folds, where b was the number of estimators we had. Now, of course, this isn't really practically helpful because we usually can't just magically have b times more data. But it does hint at the power of ensembling. By combining multiple models or estimates, we get more stable results without introducing bias. So is there anything we can do to reduce variance with a fixed size data set? So let's consider for a moment two small data sets, S1 and S2. So S1 has samples 0.4, 1.0, and 1.6, and S2 has samples 0.5, 0.7, and 1.2. And so using the empirical mean estimator, we can see that this would give us estimates of mu hat 1 equal to 1.0. So just add those all up, gives us 3, divide by 3 gives us 1. And then mu hat 2 is going to give us 0.8 following the same process. But let's notice something interesting. So the total inside the brackets for mu hat 2, that's 2.4. That could actually be composed by reusing elements of the first data set. So for example, we could take the value 1 twice and the value 0.4 once. And that would give us exactly the same answer as we got with the true mu hat 2, with that true estimate for the second, with the true estimate of our mean. So this idea of reusing data gives us a way to explore variability even without gathering new data. And so this is the key idea behind bootstrapping. And so we're going to mimic the variability of drawing more samples from the population by resampling the original data with replacement. And so each bootstrap sample contains a slightly different mix of the data points. Some are going to appear more than once, others might be left out, exactly like what we saw here. And so as a result, we're going to get multiple possible outcomes, which is going to help us measure the variability in our estimator, like the mean. And so bootstrap sampling works because it assumes that the original data set is a good approximation of the population. And so even though each bootstrap sample contains some bias, it's not a perfect copy of the original data set. The law of large numbers ensures that as we create more bootstrap samples, the average behavior of the samples is going to approach the true behavior of the population. So to give some examples on exactly how this works, let's suppose we had a data set of X1 through X5. We could then construct bootstrap realizations by resampling this original data with replacement. So what that means is that we would still create a sample that has 5 samples in it, but we might see some samples appear more than once. So for example, in this case, X1 appears twice, whereas X2 doesn't appear at all. And so the way this is constructed is that when we draw every sample that we draw from this original data set has an equal chance of becoming the next sample, of appearing in the bootstrap realization. For another example, here X5 appears twice and X4 doesn't show up at all. Now X3 shows up twice, and again X4 isn't present. So these are examples of bootstrap realizations of the original data set. Right, so how does bootstrap sampling apply to ML? And so in machine learning, a family of techniques leverages bootstrap sampling to train multiple models on slightly different versions of that original data set. So this means that instead of training just one model on the whole data, we create multiple data sets by sampling with replacement, and then train a model on each one, and then combine predictions. And so this collection of models forms what's known as the ensemble. And aggregating the results helps reduce variance and improve overall performance. So yeah, looking at the schematic here, each bootstrap realization is a slightly different version of the original data. And so some points are going to be repeated and others are left out. And this is denoted by like dark rows indicating repeated presence of an observation. Whereas the light rows, the white rows, indicate that observation didn't show up at all in the bootstrap realization. And so each sample is used to train, each bootstrap realization is used to train a separate model. And we think of these models as the base models. And so this is one base model, another one trained on another bootstrap realization, and a third one trained on a third bootstrap realization. And so once trained, these models are then combined to make that final prediction. And then this aggregation is key because it means that we're not relying on a single model's possibly noisy prediction. We're instead combining all of them to get a stable result. And so this approach here is called bagging, and that's short for bootstrap aggregation, or bootstrap aggregating, I guess. And so bagging reduces the risk of overfitting by making sure that individual models don't get overly attached to specific patterns or noise in the data. And the variability in the training sets forces each model to learn slightly different patterns. And this is going to balance things out when their predictions are combined. And so bagging is particularly powerful when these base models, things like decision trees especially, when they tend to overfit individual data sets. So bagging is a very general method, and what that means is that it can be applied to both regression and classification problems. And so in regression, we take the average of the predictions from the individual base models, and then for classification, we take the majority vote. And so whichever class gets the most votes from the base model to become the final prediction. So in this case of a prediction in binary classification where we're predicting either -1 or a +1, then if the sum of predictions from the underlying for the base models is greater than 0, so there's more positive predictions than negative predictions, we would make that positive prediction, and it would be a negative prediction otherwise. So this flexibility, the fact that we can bag both regressors and classifiers, this makes bagging a popular and effective tool in many machine learning tasks. So how well does bagging work? So one valuable comparison point would be the error of a single bootstrap model to that of the full ensemble. And the derivation of this can be found in section 14.2 of the pattern recognition of machine learning text. So let's start by analyzing the error of a single model. So in this schematic, this is the individual model here. And so this one is trained on one bootstrap realization. And then their predictions are then aggregated to form the final ensemble prediction. And so what we're interested in is how this individual error would compare to the combined error for the full ensemble. Okay, let's suppose that the target that we're trying to predict, T, we can model that as the prediction from one of these base models. So we'll call the prediction from one of our base models y sub e plus a residual epsilon. And so that this error term that captures how far off the model's prediction is from the target at any point x. And so for a single bootstrap model, the error is just the difference between the target and our prediction. And the squared error, that squared error is the expectation of the squared differences between the target and the prediction of and a single model prediction y sub e. And so this gives the single model's sum of the squared errors. So and that's simply just the squared error. So nothing special there. Sorry, simply just the squared error. And then the average error across bootstrap models, if they were acting individually, that's simply the mean of the errors, across those models. And this is expressed as the expectation over all the individual model errors, and which reduces to exactly the same, as a single model acting on its own. So, okay, so we've computed the error for a single base model, but what about the ensemble? And so recall that for this regression problem, we're interested in an ensemble. We're interested in an ensemble that returns the average prediction across base models. And so if that's the case, then the expectation of our squared error that now grows with the difference between the target t and the ensemble average prediction. And so since the ensemble gives an average prediction over all the base models, we're going to express the ensemble prediction as 1 over e of the sum of each of the individual model predictions. And so big E, that's the number of models, and y sub e is the prediction of the eth model. And so this means that we're looking at the expectation of the squared difference between the target value tx and the ensemble average. And so we can rewrite this prediction y sub e for each model in terms of in terms of the target tx and the error term epsilon sub e. And this means that each prediction can be composed as the true value minus the model specific error. And so, yeah, substitute that in the previous equation gives us that there. And so we can now simplify this further because the true value t of x that's present in every term of this sum. And so we can actually factor this out and see that the difference involving t of x would actually cancel. And so we're left only with the error term. Okay, now so we can see that we're squaring a sum, and squaring a sum like this, that's going to produce a double sum. And so this double sum that captures not just the individual error terms, but also the interaction between pairs of errors from different models. And so now we need to look at the cross products between these errors to understand how they contribute to the overall variance. And so by linearity of expectations, we know that we can rewrite this expectation over the sum, as a sum of expectations applied to each pair of errors. All right, so now the challenge is to analyze how these errors interact and affect the final prediction when averaged across multiple models. And so that the key is really gonna lie in understanding what happens to the error terms in that double sum, in this double sum here. So this double sum is going to contain two types of terms. So there's the diagonal terms where I equals j, and that's going to represent the variance of the individual model errors. And then we're going to have the off diagonal terms when I is not equal to j, and that's going to represent the interaction between errors of different models. And so let's explore, for the sake of argument, what would happen if we made two assumptions. So let's assume that the mean of the errors is 0, and then let's assume that the errors are uncorrelated. And so if the errors of different models are uncorrelated, then those interaction terms here, they're going to vanish. And this happens because the expectation of the product of two independent errors is 0. And so the expectation of this term is 0. when I is not equal to j. And so what's going to remain are just those diagonal terms, which sums the variance of individual models' errors. And because we don't know, we don't expect any one model to have more error than another. The expression inside this sum here is just going to be big E times the error of any one model. And so with big E models in that ensemble, the final expression is for any final expression of any final expression is the error of any one bootstrap model divided by big E. And so that's for the ensemble. And comparing this to one bootstrap model acting alone, we say that the error of the ensemble reduces the error proportional to the number of base models in the ensemble. So this is a pretty dramatic result. Does it actually hold up? And so the answer is somewhat. The result critically depends on this assumption that we've made of decorrelated errors in order to get rid of those diagonal terms. In practice, with bootstrap sampling, the errors are not going to be perfectly decorrelated, and so we won't achieve this extreme reduction. I attempted to play around with this a little bit on my own. The ESL text claims that the error correlations for linear estimators are relatively high. And so if that's the case, then this would mean that such models are poor candidates for bagging. And so I explored this idea on my own empirically in this figure on the left. The dashed black curve depicts the true underlying function, which in this case was a fifth degree polynomial from which I generated some noisy samples denoted in these black plus markers. The solid pink line, that's the maximum likelihood estimate fit on the whole training data set. And each of these faint pink lines here, that's the prediction of a bootstrap model fit to different bootstrap realizations of that data set. And then the dashed pink line is the aggregated behavior of the ensemble over 100 such base models. And so what I noticed was that the ensemble fit of the conventional model, the ensemble fit and that of the conventional model are almost identical. And then I repeated this process 100 times and compared the total error on a trial by trial basis between the conventional model and that achieved by the ensemble aggregate. Yeah, so in this case, the test in the next slide, I'm going to show a scatter plot. But the x-axis here, that's the test error on the conventional model, and then on the y-axis is the test error on the ensemble model. And then the dotted line here that depicts where points would fall if these two strategies produced identical errors. And so if the ensemble outperformed the conventional model, then we would expect points to show up in the lower right-hand corner. Whereas in the other hand, if the conventional model outperformed the ensemble, then we would expect points to fall in this upper left-hand corner. And so the data revealed that the ensemble was no better than the conventional model. Points tended to fall right on this line of inequality, and might have actually been slightly worse, at least in this empirical exploration that I did. So there's quite a few that have really missed the mark. And so that this is consistent with the claims in the ESL text. My purpose of showing you this today is just as a warning that there are some models are not good candidates for bagging. And to do a sanity check on your own if bagging, if you're considering bagging, you might need to consider what model you're working with or what hypothesis class you're working with before going down that road. Yeah, so linear models don't seem to be the best candidates for bagging, but decision trees are really popular really popular. And so the intuition is because of how a tree is built by that recursive partitioning process. And so the idea is that small variations in the training data set, like what would happen with bootstrap sampling, they can produce effects that cascade down the tree. That would significantly decorrelate the errors from one bootstrap tree to the next. So if you had a slightly different training data set, then you might get a different threshold or maybe even a different feature selected at the top layer of the tree. And then that would have, what would that mean for subsequent features selected and subsequent thresholds split as we work down the tree? And so decision trees are such a popular choice in ensemble methods that the community has found new ways to decorrelate the errors even further. Specifically, in bootstrap sampling, we've been emulating the variability of resampling from the population by resampling observations. So, resampling the rows. But we might also consider injecting variability along the input features so that each model gets a different representation about which features to make decisions. And so this is the idea behind the random forest algorithm. And so the random forest algorithm decorrelates both the samples and features. And so like bagging, it's going to build many decision trees, each trained on a bootstrap version of the training data. But the key innovation in random forest lies in how it selects features for each split. And so at each node, instead of considering all the predictors or all the features, the algorithm is going to randomly select a small subset M, a small subset of M predictors from the total pool of P predictors. And so that this randomization at every split, that's going to introduce diversity among the trees and ensure that they're not all influenced by the same features. So the graph on the right here shows how limiting the number of features provided to the decision tree algorithm affects classification error. And so the x-axis represents the number of trees in the ensemble, and the y-axis shows the test classification error. And that measures how well the model performs on unseen data. And so these three lines here, they correspond to different values of M, where M was equal to P, so they the same number of features, or at each. So when M is equal to P, that would mean that at every node, we give access to the decision tree algorithm every feature, so it can select from every possible feature on which to split. And some other choices are M equals P over 2. So we're giving the model we're allowing the decision tree algorithm to pick between half of the available features in the data set. And then M is the square root of P. So that the blue line, that's a simple, this orange line here, that's a simple bag tree, and that's going to have access to all the input features. So what we can see is that as the number of tree increases, the classification error tends to decrease, but at different rates for the three curves, and they bottom out at different lower points. We can see that the green curve of M is the square root of P. That seems to show the best performance, as that demonstrates the benefit of selecting a small random subset of predictors at each split. So this feature selection strategy might sound counterintuitive at first. Like why are we ignoring most of the predictors when making splits? But the rationale is actually quite clever. And so the idea is that if a strong predictor dominates the data set, so if there's one single feature that is really is a really strong predictor, many of the trees in a bagged model would end up using that same predictor for their top split, and that's going to result in highly similar trees. And so when trees are correlated in this way, averaging their predictions doesn't reduce the variance as effectively. But in random forests, by forcing each split to only consider a random subset of the features, the algorithm is going to ensure that the trees become more diverse, and that's going to lead to lower overall variance when their predictions are average. And like we discussed, not every estimator is gonna benefit from this kind of randomization, but it turns out that random forests do exceptionally well with this approach. And so by decorrelating trees, the algorithm's going to achieve a significant reduction in variance, outperforming bag trees and providing robust predictions. And so this is why random forests have become a popular choice in machine learning, because they strike a really great balance between bias and variance while remaining computationally efficient. So another way of thinking about these decorrelated errors of decision trees is that they have high variance. They have high variance and therefore low bias. So they live in the upper left-hand corner of this plot. And so that makes them good candidates for bagging because bagging reduces the variance, which is the main source of error for these models. And so if we instead had a model that had low variance, like in the lower right-hand corner of the plot, bagging would be of limited use. And this is because there's less room for improvement in terms of variance, and because bagging has little effect on bias anyways. And so it's not going to help us get any closer to that ideal sweet spot in the lower left-hand corner that we're aiming for. And so if we find ourselves instead in this spot, what we want to do is target bias directly. And so this leads us into the next part of the talk. How do we build ensembles to target that bias factor? And like I alluded to in the introduction, the way we build models to reduce bias is sequentially. So we build a base model using the data set, and then use its performance to inform how to train the next base model. So effectively to fill in the gap for where it did poorly. And so now let's get into the specifics. What this means is that one base model has control over the relative weighting of points used to fit the next model. And so this is like having points show up in the training data set multiple times, but the number of times it shows up is determined by the previous base model in the ensemble. Like I said, the ensemble model is going to incorporate predictions from all the base models, but the aggregation is going to be a little bit more nuanced than the simple weighted average or majority vote that we saw with bagging. So the idea is that boosting combines weak models, models that are only slightly better than random guessing, and turns them into a strong predictive model. So yeah, the idea is that we're starting with base models that are weak, also called weak learners. So these are very biased estimators. But then by building this kind of chain, we're going to create an ensemble that reduces the bias. So a significant ensemble method for boosting is called ADA boost. And it was originally developed with binary classification in mind. So this figure here was taken from the PRML textbook. And so these Y1 through YM, they denote the base models of our ensemble. And so each one of these, that's going to be trained using our data set, but each observation in the data set is weighted by some amount. And that's going to determine the extent to which that observation can influence the learned decision boundary. So that this blue line here, that indicates that a given base model is determined by some weights, some set of weights W sub n. And the superscript here denotes that this set of weights is for the first base model or the first base learner. But these, and then the second set of weights, that's for the second base model, and the nth set of weights, that's for the nth base model. But here's the catch. So apart from the first model in the series, the very first base model that we built, these weights, they're determined by the previous classifier. Yeah, so the weights used to train the second model in the series, that's determined by the first model. And specifically, AdaBoost is going to decrease the weight of points that weren't correctly classified and increase the weight of points that were incorrectly classified. So the next model can focus on what its predecessor couldn't get right. So we'll talk more about that as we go. But importantly, this is a purely forward process. So we're never going back and adjusting earlier models once they've been added to the ensemble. And so the predictions from all previously built models, they get added together as the ensemble grows. And so each new model tries to correct the mistakes of earlier ones by fitting the weighted errors. And so this process continues until we trained the desired number of M models, which is a hyperparameter controlling the complexity of the ensemble. And then the final prediction, Y sub M of X, that's a weighted sum of the individual model predictions. And then we apply a sign function to determine the aggregated prediction. And so this is a second set of weights, kind of a that weights the predictions of individual models. So alpha here is the weight given to any one base model's prediction in influencing the prediction of the ensemble's prediction. And so what makes boosting unique is that unlike bagging or random forests, it reduces bias, and then also by fitting models that depend on each other. And so in boosting, each model builds on the work of the last. But in bagging, each model was actually independent of one another. With the caveat of there being correlated errors. And so before we get into the math, let's look at this another way and get a sense of the high-level behavior of the AdaBoost algorithm. So let's consider a binary classification problem with a simple base model that can only split on a single feature of the data. So this setup is depicted in this first panel for a data set consisting of two features. So along this axis and the second feature along here. And the positive class is in red, and then the negative class is in blue. And the decision boundary for this classifier is shown in black, and the decision boundary for the ensemble classifier is shown in green. And so this panel on the left here, that illustrates the behavior of the ensemble when M is equal to 1. So we have one base model in our ensemble. And so in this case, that base model opted to split halfway along the first feature. And that makes sense because most of the blue points are in the negative class. Most of the blue points in the negative class are on the left, and most of the positive points are on the right. But we can see that it made a few errors. Specifically, this decision boundary would misclassify this point as well as this point, and then a few on the positive class, like this one would get misclassified as well as this one and this one over here. And so it's these misclassifications that are going to get reweighted, are going to reweight the data to train the next classifier. And so in this second round, that's when M equals 2. This is where the points get reweighted. And so the relative weight is denoted by the size of the respective circles of the data points. And so whereas in the first round, these circles all had the same radius, now we see that they're different sizes. So the misclassified points that we had originally, they've got a larger radius, so they're weighted very heavily in training the next classifier. Whereas everything that was that the last classifier classified correctly, those are downweighted. They have a relatively lower weight. And so we can see now that the decision boundary of this classifier in black, that's distinct from the ensemble in green, because we're taking a weighted average of those predictions. And so in this case, it still decided to split on the first feature, Perhaps there's still a residual effect because of all the samples from the first round. And it would still misclassify these negative samples, these blue samples that belong to the negative class. And so in the third round, the points are reweighted again, and so those two remaining misclassified points are now going to dominate the objective. And so now the base classifier decides to split on the other feature, and the decision boundary is now a jagged line drawn through the space, closer to what we would expect of a decision tree. Okay, so now we can get into what AdaBoost is doing under the hood by looking at the algorithm. And so the first thing the algorithm does is initialize the weights for the data points. And so at the beginning, all the points are given equal weight, and that means that each data point is equally important for the first base classifier. It's reflected here in this equation of W sub n sub t is equal to 1 over n for every n from 1 to n, and then where n is the total number of data points. And then in the main loop is going to run from m of 1 all the way up to big M, where m is the total number of base classifiers that we've decided. And then each iteration, the algorithm is going to fit a new classifier, y sub m of x, using the current data weights, where that's the current data weights there. And so each classifier is going to be parameterized by some arbitrary set of parameters theta. And we want to, and then fitting a classifier is going to, in general, involve finding the parameters theta that minimize the loss. In this case, a weighted sum of misclassifications. So here, this is y sub m comma theta x of n. That's the prediction of the base model for a particular point x of n, and we want to find out when those predictions don't match the target values, don't match the target value t of n for a particular point. And so there's this indicator function that's going to be 1 when there's a mismatch between the prediction and the actual target, and then we're weighting those misclassifications, weighting those misclassifications according to on a point-by-point basis. And so yeah, this whole expression here that's simply minimizing a weighted objective. And so once that new model is changed, once we know what those parameters theta are that minimize this objective, we next calculate the weighted error rate epsilon sub m. And so this new error rate that reflects how well the current classifier performed with the weights assigned to previously misclassified points. And then we compute alpha m, which measures the importance of the current classifier in the ensemble. And so classifiers with lower errors are going to get larger alpha values, and so that means that their predictions are going to carry more weight in the final decision. And then last but not least, the weights for the data points are then updated based on how well the current classifier performed. And so points that were misclassified get their weights increased, ensuring that they receive more attention in the next iteration. And in this way, each new classifier focuses more on the difficult points than previous classifiers struggled with. And so this loop is going to continue until all n classifiers have been trained and added to the ensemble. And then the final output, y sub m of x, that's that weighted combination of all the individual classifiers' predictions. And so AdaBoost carefully balances the strengths of each classifier and emphasizes the most accurate ones, which helps the ensemble outperform any one individual component. All right, so we talked about both bagging and boosting today, but are these equivalents? Is one better than another? But yeah, another problem is that they kind of have similar names, and I remember when I first encountered this material, I was a little bit I would tend to mix them up, and so to really help discriminate them in your mind, I'd like to anchor them to some analogies that potentially some of you are familiar with. I might be aging myself a little bit by referring to this, but for any of you in the audience that are familiar with Rick and Morty or have watched those shows, bagging to me is a little bit like the Horde of Cronenbergs. And so, for those of you who aren't familiar, Cronenbergs are from the Rick and Morty universe. They're these, gross and chaotic creatures that, on their own, are kind of unpredictable and might be kind of useless. But then when they come together as a, swarm or ant or army, they're kind of this fearsome force. And then so this really is aligned with this idea of bagging because each individual model in bagging, like decision trees, is really quite chaotic and noisy. Each tree might be overfitting a specific subset of the data, but then when you ensemble many models together, their averages are going to their errors average out, and you get that robust, stable prediction. It's a lot like how, Cronenberg's took over the world and actually forced Rick and Morty to abandon their universe for a new one and have to find a whole new family. And so, yeah, along this line of diversity, just as Cronenbergs are wildly different from each other, we really want to use bagging on models that that do have extremely high variance. We want the bagged model to have base models that are very different from one another in order to get the maximum effects of bagging, in order to see the maximum effects. On the other hand, boosting in my mind is a little bit more like the Mr. Meeseeks phenomenon, again from the Rick and Morty universe. And so in the Rick and Morty universe, this Mr. Meeseeks character is someone that you can summon to help you with a specific problem. So you're given this box, you press a button, and then he appears, and you give him a task, and he's going to solve it, and then that's the entire purpose of his short existence. And this works pretty well, but then in one episode, there's this character Jerry who has a lot of he has quite a bit of problems. He tends to struggle with a lot of things. So this character, Jerry, summons Meeseeks to help him take 2 strokes off his golf game. And then the first, there's this Meeseeks, he fails to fully achieve this goal. But then so when he fails to help Jerry with his golf game, he summons another one to try to help out. And then this didn't work either, and eventually there ended up being a large horde of these Mr. Meeseeks all trying to help out the last one that summoned them. And they work sequentially, each one trying to focus on what still needed fixing. And they didn't stop until the job was done. And so boosting is a lot like this because it built up these weak models in sequence. Each model tried to fix the mistakes of the previous one, just like the Meeseeks tried to help with tasks that the earlier Meeseeks couldn't complete. And so whereas one Meeseeks might get part of the task done, a team of them together actually finally managed to get it done. Just like boosting aggregates the contributions of multiple weak learners to create a strong final model. And so this, so how do they compare in practice? So this figure here is taken from the Introduction to Statistical Learning text. And what they did was to compare boosting and bagging on decision trees. So on the x-axis here, that's the number of trees in the ensemble, and then the y-axis is the test classification error. And so they considered the random forest algorithm with a square root of p predictors in green, and then two boosted decision trees with a depth of 1 and 2. So a depth 1 decision tree, that's simply a decision stump, so it can split on a single feature, and that's it. And then a depth 2 decision tree is allowed one more feature after that. And so the random forest algorithm that's shown in green, that that achieves a minimum error at around 2,000 trees of about 12% classification error. But then the uh, boosting achieved even lower lows than that again. So in practice, boosting is often favored over bagging. Boosting tends to give us an edge over bagging. All right, so that brings us to the end of this lecture. The quick summary: we encountered that the bias variance decomposition in this lecture. We started off by formalizing these kind of hand wavy ideas about the bias variance trade-off through a decomposition of the test error to allow us to interpret test error as a contribution of three terms. We then also saw how to implement bagging techniques to aggregate models and reduce variance without increasing bias. We also encountered some boosting methods and boosting methods that build up ensembles sequentially to attack that bias problem by focusing on reducing errors that the previous model had. And also we presented these two side by side. And so we saw the use cases in which one might be more appropriate than another. We also encountered the random forest algorithm, which combined standard bagging of producing these bootstrap realizations of the data set together with subsampling the feature sets to further decorrelate the decision trees. We also evaluated the impact of ensemble size on test error reduction. So we've made some we encountered this analytically, theoretically, and then also saw this empirically in the case of decision trees. As we increase the ensemble size, we do tend to decrease test error up to a point at least. And then last but not least, we saw that these are very general methods, right? They work for regression and classification tasks. And so this makes sense to apply these methods to both, to either. All right, thanks for your attention. We'll see you back here again next time. We'll be talking about expectation maximization and Gaussian mixture models.